Functions. We're going to end chapter 2 today. Today we will look at combining functions. We'll look at sums, differences, products, and quotients, and then composition of functions. Shouldn't be too hard of a day. First, let's look at sums, differences, products, and quotients. If you have two functions, what we're simply saying is that you can add them, you can subtract them, you can multiply them, and you can divide them. The important thing here is to make sure you know domain, and we've already gone over that several times, so that's an advantage for you. So we're going to look at the domain of G, and we're going to look at the domain of F, and then we're going to take the intersection of these domains, and we can do the same thing with the difference, the product, and the quotient. Now, the only thing we have to add to that is to remember that if we have a quotient, we cannot divide by 0. So for instance, let's say we take these two. We take f of x is 1 over x minus 2, and then we take g of x is the square root of x. And we're going to add them, subtract them, multiply them, and divide them. Then after we do that, part B, we're going to plug 4, as long as it's in our domain, into all of these brand new expressions to see what the value will be. So if we look at the top, we see that the domain here can be anything we want except for 2. Because if I plug 2 in for x, I will get 0 in my denominator. So that tells me that it's x such that x will be, oh, I'm sorry, let me bump up here. X such that x cannot equal 2. So this is for f. Now the domain of G is the square root. So everything under here, since it's square root and it's even, has to be greater than or equal to 0. So the domain of it is x such that x is greater than or equal to 0. So here we have the domain for both of them. We put those together. So I would have x is greater than or equal to 0 and x cannot equal 2. Now, if I were to write that in interval notation, I would start at 0 and include 0. I would go to 2, but since 2 is not included, I have to put a parenthesis, and then I'm going to union that with everything after 2 into infinity. So now we have, let's add them both together. And we simply do that. We just write the first one plus the second one. We really don't need to find a common denominator and combine them in this problem for any reason. We're just putting the expressions together. So that's it. And then you know that the domain is going to be greater than or equal to 0, but not 2, just like we just said. Okay? So again, that was the reason we looked at that before, is because we want to highlight the fact that this domain is what we have when we add them together. When I subtract them, guess what the only difference is? I'm going to use a subtraction symbol. So when I subtract them, I'm just really adding a negative. So the only thing that changes is that this is minus. I might have to maybe distribute it in if I have more than one term over here. But that's it. And the domain stays the same as before. When I multiply them, I'm going to take this times 1 over x minus 2. And guess what I get? I get this on the top and I get this on the bottom. So again, my domain remains the same, and I have x is greater than or equal to 0, but not equal to 2. And then finally, anytime that you divide, you have to double check yourself, because we know that the bottom cannot equal 0. So the difference here is that on the bottom, we can't have 0, so I cannot put 0 into this part. Now, I don't know why they have this here. I'm going to cross this out because this should only say that it's bigger than 0 now. We cannot have greater than 0. We just set, or cannot have it equal to 0 because we just said it's on the bottom. It doesn't work. So you'll want to make that change on your slide. And then still it cannot equal 2. Now, if I think about the domain that I just said that I had, 4 exists in that domain. So for part B, we said we are just looking at those expressions at 4. Oops, sorry about that little clunk. Okay, so we're just looking at the expressions at 4. So what we're going to do is plug 4 into each of those functions, and then we're going to simplify. And for the first one, I get 5/2. So I'm just plugging 4 in and simplifying. The next one, I do the same, except for I have subtraction this time. So I plug 4 in and then simplify. Multiplication, guess what? Same thing, plug 4 in. And then, and notice they have the multiplication, they have it over here this time. It doesn't matter whether you have it here or whether they would have placed it on top. You're going to get the same result, okay? I don't want that to confuse you. All right, and then that'll be 1. And then finally, for the division, I'm plugging 4 in. And I have 1 over those values, which will give me 1/4. Now, we can add, subtract, multiply, and divide graphical functions and look at them on a graph. Now, the multiplication and division is a little bit difficult, but we'll take a look at the adding right now. Here I have this function added to this function. So what am I actually doing? I'm going to change colors here. Let's see. Let's use a green. I am taking this value right here when I have this coordinate at this location, and I'm taking this space that is created, or the distance. That's not a 3. It's supposed to be a bracket. It's an ugly bracket, I know. So this distance, and I'm going to add it right here at the same location on the line, and I'm going to plot a point. And I'm going to do that for every single one of these values down here on F. So let's see what happens. So here it is. I take each distance from the x-axis to my function of f, and I come up here to g and I add that. So you can see it changed the slope because now we have it on a sloped line instead of a horizontal line down here. Composition of functions. Composition of functions is a way of taking one function and plugging it in to your domain of another function. So it looks a little confusing at first when we take a look at this right here. We're saying we're making a brand new function, so we just choose h of x. You can choose whatever you want, except you don't want to choose f and g if you're using them over here. Sometimes they will actually use for composition a capital uppercase value f, and they'll say uppercase f of x as an indication that you compose two functions to get what you have next. So you can either do it this way or you can do it this way. All right, let's take a look at this. This says I'm going to take g of x and I'm going to plug it in to my f of x. So whatever g of x is going to be my new x value. So since g of x is equal to x squared plus 1, I'm going to put x squared plus 1 into my value for f, and that means since my f, again, let's remind ourselves, f of x is the square root of x. Now, instead of it being the square root of x, it's the square root of x squared plus 1. Why? Because g of x is x squared plus 1. And they use the symbolism of putting it into a machine again. You're going to put x into the machine of g. You get x squared plus 1. And now you're going to put that function itself into f. And then you get your output. So here's another way. Some of you might like this visual interpretation better. So in general, given any two functions, f and g, we start with a number x in the domain of g and find its image. And when we call image, we're saying we're going to find its range. If this number, g of x, is in the domain of f, then we can calculate the value and put g of x into the function of f. The new result, which they are calling right now h of x, which could also be called capital f of x, uppercase or capital was what we called these when we studied growing up in elementary school, which was only a couple years ago. And we call this a composition. Now, this composition of functions is represented by this symbol right here. So whenever you have this little open circle, that's not somebody that forgot to fill it in and mean multiplication. That means they're taking composite functions. Okay, and another representation of what we're doing here is we're taking the domain of one function, we're putting it into that function, then we take the value of that function, and we put it into this function. So let's find the composition of functions. So now I have f of g and g of f. What's the difference between these two? I have f of g here. I have g of f here. I will tell you this, they may not be the same. Okay, so what this one means is that first I'm going to, and I see I'm going to switch to black here. Let's hopefully see if I can write a little better today. I'm going to take my f function and I'm going to put in there g of 5 for the first one. Okay, so this is this. And then my second one, I'm going to take f of 5 and I'm going to plug it into my g. So very often these are going to be two completely different answers. Sometimes they might be the same, but don't anticipate that. Okay, so those are those two. Okay, so here we have this now, like I just said, and we're going to plug g of x, which is defined at the very top, up here, there we go, g of x into our f of x. So that would look like this. The next step would be to take that x minus 3 and plug it into my f of x. Well, this is the second one. Okay, so my end result for the first one, which is f of g of x, I'm going to put that here. If I have f of g of x, or g of 5, well, no, not yet. This is just g of x. F of g of x is right here. Okay, and we'll want to talk about the domain of this as well. So we see that this is a polynomial function. So our domain here will be all real numbers. So we can't forget about domain. Domain equals all real numbers. All right, so now let's look at the second one where I take g of f of x. So I'm going to have f of x first, which is my x squared, and I'm going to plug that into g of x. So you can see two very different things. Here I subtract 3 first, and then I square it. And here I'm going to square it and then subtract 3. This is also a polynomial function, so it's also the domain of all real numbers. Yay, we don't have to do something different there. Okay, so now I'm going to substitute my value of 5 into my composited function. And what I need to remember is that my g of x is x minus 3. So I'm going to plug 5 in for x, and I will get my 2. And then that value I'm going to plug into my f of x, which was x squared. So I plug 2 into x squared, and I get 2 squared, which is 4. Now let's take a look at the composition of g of f, which we're looking at it at 7. So first, I'm going to take 7 and plug it into my f of x. Now remember, this is my f of x right here. So I'm going to plug this in first. So when I plug it in first, I will get 49 because 7 squared is 49. Now I'm going to take that value and plug it into my g of x, which is x minus 3. So I just take 49 minus 3 and we'll get 46. So you can see again, like I mentioned before, that in general, the composition of f of g is not the same of g of f, okay? So it just means that you're going to apply one first and then apply one second, plug one into the other. So I can have the composite of more than 2 functions. I could have the composite of 3 functions. I could have the composite of 10 functions. So you just do them in order. So here, I'm going to take whatever value is first, which is, or, I would say closest to the x this way when I say first, so right here. And I'm going to take h of x first. After I get that value, I'm going to take g of that new value that I got from h of x, or new expression. And then finally, I'm going to take f of the expression that I get once I plug it into g of x. So here's an example. I have 3. I have x over x plus 1. I have x to the 10th, and I have x plus 3. Now first, let's take a look at domains of each of these. You should always check your domain. And I noticed that the first one is a rational expression. So that means 0 cannot go on the bottom. So here I cannot have -1. This is a polynomial, so it's just real numbers. And then the second one is also a polynomial, so it's real numbers as well. Okay, so let's take a look. So as we said before, we're going to take h of x first and plug it into g of x. Then we'll take that and plug it into f of x. So here we go. Here's our f is equal to g of x plus 3, because x plus 3 was what h of x was, or is, I should say. Not was. I don't think it's gone. It's still right here. Okay. Now I'm going to plug this value into x to the 10th. So instead of x, now it's x plus 3. And I'm plugging that into g of x. And then finally, wherever there is an x in f of x, let's look back up here, that would be right here in the front and right here in the, well, I could say on the numerator and in the denominator. I'm going to put this value in for x. So it will go on the numerator here, and it will go in the denominator here. Now, we've used compositions to build complicated functions from simpler ones. In calculus, it is useful to be able to decompose the complicated functions into simpler ones, so going the other way around. So in order to do this, it's best to talk it out. So if I said to you, and I was going to give you some values to find what values would be for this. And notice here, they're starting with a capital F, as I mentioned before, because they're saying this is a composite of functions. So I would say, well, I take a number and add 9 to it. Then I take the 4th root of that. Anytime you say then, you could actually change it to a composition. So if I were to write 2 composite functions for this, I could say that my g of x was take my value and add 9 to it, and then take the 4th root of that. So if I composite f of g, I will get the 4th root of x plus 9. This is a little bit of inverse thinking, but after a little practice, you'll get good at it. So the first solution, I'm going to take my x plus 9 in, and then I'm going to take the value or the expression that I just received of x plus 9, and I'm going to plug it into my 4th root. And that'll give me my composition. So that is it for this section. So we have one more section to do, and then we'll start preparing for the exam. So I will see you soon.